So whenever you open AutoVectus, you'll be presented with this splash screen which allows you access to all the main AutoVectus workflows. But for processing your MALDI data, you'll want to go into the AutoPhaser tool for phase correction and producing absorption mode spectra. And so we open that by clicking the AutoPhaser icon. And that then brings us into the AutoPhaser user interface. The way you run batch processes in here is, first of all, we'll phase a single file member of the batch, and then we will run the batch where it will apply all the main settings to all the files in the batch. So we set up the parameters for an individual file on the File and FFT tab, and we choose the file that we want to process by clicking this Browse button. So here you can see we have a folder containing a Bruker file. If we open that folder, because all Bruker files are folders, and then click Current Folder, it will select that folder and it will appear in the file path here. We'll set the file type to Bruker, obviously, and it's not a heterodyne file, so we'll leave that off. Down in the next row, we can set the number of zero pads and the mass range. And these may vary for an individual file, but you can edit these here. Bruker files can be saved in two different formats. So there's the FID format, which contains just a single transient, or your files will be in SER format, where they contain a series of multiple transients. So we'll keep it in SER format. We don't need beast mode here because these aren't enormous files. They're only 4 megapoints long, even after zero padding. We could add more zero pads if you wish. Apodization, I've tried lots of different apodizing functions. I would go for the DPAC one, which is the asymmetric apodization with a fraction of 0.4. This pre-existing phasing solution is how AutoPhaser identifies a candidate phase correction function to optimize across the spectrum. In recalculate mode, it will choose a small part of the spectrum and brute force fit a phasing function to that, and then extend and optimize it across the spectrum. We have other options where we can save previously saved phase correction functions. Down here, you could just use the current phase correction function, which is the one for your immediately previously processed file. Or we'll choose this option here just now, which is ab initio values. And that's because the Bruker files contain information about how the ions were excited inside the RCR cell, and AutoPhaser can use that to generate a candidate phase correction function for optimization. The last thing we need to do is choose which one of the serial files to process. There are, of course, a lot in each file, so you could choose one randomly, but because some of your spots are blank, you might therefore accidentally choose a blank spot. So I would recommend using the Smart Sum tool down here, which I'll engage just by clicking that. And now we have all the parameters in place that we need, so we can just start the phasing process by hitting the Begin button. And that immediately pops up the Smart Sum tool, which will show us the total ion abundance and base peak intensity for all the points in the file. The base peak is shown in red and the total ion abundance in yellow. They are normalized to a maximum of 1, so we can see them both on the same scale. And we can see here we have some files like these which have data in, and other files like the ones that plot down here at zeros, which are clearly the blank spots. So we can choose a file that we want to use as this initial file just by zooming in using the zoom tools that are available here and choosing a nice high intensity file. So we can choose 47 and hit enter. And now AutoVectus will load that transient, Fourier transform it into magnitude mode. We can see that here. This is to identify peaks that will be used for phasing. Once you've got parameters that you need, you can just keep this set. The green peaks are the ones that are going to be used for phase correction function generation. Here you can set the signal to noise. We can set that to 3, for example, and then accept peak definitions. And then it will try to apply that candidate phase correction function across the whole spectrum. That little bit where you saw the line moving up the screen, that was the genetic algorithm optimizing that phase correction function. And so it's now complete, and we can see the phase corrected file. And again, we can choose one of the zoom tools to zoom in and see. This seems like a good example, some of the data. So the magnitude mode spectrum is in red and the absorption mode spectrum is in green, which I guess is why you're interested in using it, because of this improvement in resolving power. One important thing we can look at if we go to the Phasing Excellence tab is how well that file was phase corrected. You probably won't need this output too much, but this one here is important. So here we can see the residual phase error on all the peaks that we use for phasing in the spectrum. And we can see they fit within a nice discrete band, and this blue line, which is the final phase correction function after all the unwrapping, fitting through them quite nicely. If this view looked like this one with points scattered all over the place, then that would imply that the file hadn't been phase corrected properly, and that's something you can look out for when doing batch processing. But in this case, this seems like a reasonably good result. We've got a small phase error on all the peaks in a discrete band across the middle, and they broadly fit to the final phase correction function well. So we can go back onto the main tab now. You can see the phase corrected spectrum. If you're happy with how that has been produced, then you can go on and set up the batch process for processing all the spots in the file. And we do that on the batch process tab. It will automatically detect the peaks in the spectrum, but you don't have to worry about that, so you could just leave that at the default setting of 3. You will want to set your default data type to save to this one, AFT as ASCII XY file. You have a number of different options in here, but this is the one you're going to want at this stage. And then to start the process running, we do phase all files in folder, which will pop up the smart sum screen again, but here we're going to use it slightly differently. We want to process all the spots, so in spectrum to smart sum we won't put in a single one. In this case we'll say 0 to 400, and you'll see that some of the points are highlighted in green where the others are not, and that's because I've set limits here that if we zoom in to say this region here, these points which have very low intensity, these are likely to be the blank transients or the ones that wouldn't process properly anyway. So I'm saying if the base peak chromatogram or the base peak data is less than 0.3 and the TIC is less than 0.5, then we won't process those ones. So they've got to be above those limits in order to be included in the list of spots to be processed. And you can change these parameters to suit the data when you get more examples to test with. But in this case, these are the files we're going to process, and so we can start the batch processing by hitting this button here, and then AutoVectus will then go through that batch one file at a time. So there's phase correcting the first file, and then it will undertake a peak detect on it, because most people want a peak list output, whereas you want the spectrum, and then saving the data to the XY file. And then it goes through all of them in turn. You can see on the batch process tab number of files left to process. It'll show in a minute. So 227 files left to process. And you can, on this tab, oops, just have to wait till I can click on the screen. Oh, they're processing too fast. I'll be able to show you this at the end if necessary. Oh, come on. There we are. So up at the top of this table, you can see the files as they process. So here for you is the spot coordinate. I just move that over to the side. That's just the serial number in the tab, in the file, sorry. The figure of merit is how well the file has been processed, and that is largely dependent on the number of peaks in the file. But as all your files are broadly similar, you would expect all those figures of merit to be broadly similar for the files you're processing. If you see some that are significantly different, then I would be suspicious that that file hadn't phase corrected properly, and I'll show you how you can review that at the end of the batch run. As the files are processing, you can also move to the Phasing Excellence tab. Just wait for that one to disappear. There we go. And so you can see down in here the residual phase error on each file as it's processed to see whether they are processing correctly. But certainly for the example file you sent, they all process fine. So I will stop the screen recording now, and I'll come back once it's finished processing all these files. So the batch has finished running, as we can see here, and we can see all the results on the MS Image tab. So here's the complete phasing output table, which we could copy and paste to Excel from here. But if we open up the folder that all the XY files were saved in, we can see we have a text file, batch phasing coefficients. So this gives us, if you open this up in Excel, it will give you the same information that's on that table, including this list here, which is the list of the figures of merit. So when you run a large batch process, I would recommend opening that file up in Excel and looking for files that have anomalous phasing figures of merit. In fact, we should just probably do that. If I close that down. Let's open up a new Excel file. There we are. So we can see our figure of merit column. An easy way to do that is just to use the data bars, and then you're looking for any which have an anomalously low value. So M4, which is 0173, 0P9224, and P5. But they still seem relatively close to the ones on top, so I don't think there's any particular issues here. And yes, as you saw in the folder, all the XY files are here, and these are the ones that you'll need to import into your downstream process. So there was one other thing I thought you would be interested to see, and that is for the situation where you can identify that one or more files during the batch run doesn't appear to have phase corrected properly. You can process those files manually and export the XY data manually as well. So if we look down the list of the files that we recorded here, this file P5, so 379, didn't appear to process properly. Sorry, 379. So we can put its serial number in this box here, and now because SmartSum is off, it will just process that file. So we hit begin to start. It'll do the peak detect. Accept that. Oh, it's gone to recalculate mode, but I'll show you that anyway. So in recalculate mode, it will automatically identify a region of the spectrum that it thinks can be brute force phase corrected, and then it will extend that across the spectrum. So normally all you have to do is hit accept, and that's it, just extending that and optimizing it across the spectrum. If we go here first, we can see the residual phase error, so that looks good now on this file. And if I zoom in, we can see the resulting absorption mode spectrum. This peak here, incidentally, has an odd shape, and I would suggest that's probably not a single peak. So there may still be unresolved components in this spectrum. If you want to export that data, if we go to the spectral info tab, we can save spectrum or peak list. So that takes us here. We can just save it as an ASCII file. You'd have to name it with the serial number or the point coordinates, whatever. But that's how you save a file manually, should you want to do so.